Okay, so today I want to discuss with you density matrices. Until now, all our theory was expressed in terms of states, okay? Given a state, you can study time evolution, okay? So for instance, obeying a certain differential equation, okay? Unitary evolution and so on and so forth. And given a state, you can measure expectation values, things like this, with an operator. Unfortunately, that's sometimes too much. Knowing the state is a little bit too much, because there are experiments in which you don't quite know exactly the state. Let me show you one simple example where this is obvious. Suppose that you go back to the Stern and Gerlach experiment, okay? You have this oven, this furnace, okay, which emits the silver atoms. You just take a beam of these things, okay, and then you go through the apparatus, and they deviate, okay? And as you know, you get half of the atoms deviating up and half deviating down. Now, this result is true, this 50% distribution, no matter how you rotate the apparatus, okay? So if you now ask yourself, well, but then what is the spin state of the atoms entering the apparatus? Is it a definite spin that I should imagine be the wave function of the atoms there, okay? Remember, the wave function will be some orbital part, okay, times a spin part. Neglect any possible spin orbit term, okay? Now, you might ask yourself, what is the spin part? Well, the spin part in general might be not up or down, but might be some combination of up plus down, okay? This is the most general spin state you can think of, all right? But now you know that I can always select these two things to be really such that they are cosine of theta over 2 plus sine theta over 2 times possibly a phase, okay? Why is that true? I mean, after all, alpha plus and alpha minus are a general complex constant. But I know that the sum of the two squares should be 1, okay? So one obvious thing is to have one a cosine and another a sine, okay? And indeed, that's the case. An overall phase doesn't really matter. You can put it here. And there is a phase, a relative phase between the two, which I call I phi. And in this second form, you recognize what this is. It's a spin state, a spin eigenstate in the direction n. More properly, is the plus 1/2 spin in direction n, where n is just given by theta and phi, okay? So the most general spin state, obviously, is an eigenstate of the spin in a certain direction, okay, which is given by some theta and some phi. All right? Well, but if this is true of the spin state of all atoms coming in, then I might search in the space of the theta and phi for the precise angle theta and phi, which is such that the spin state is eigenstate of that angle. And in that precise location, I should find, therefore, 100% of the atoms going in one spot and 0 in the other. Is this clear? So if the spin state, I repeat, if the spin state of the atoms entering was really of this form, then I've proven to you that this should be an eigenstate of the spin in a certain direction. And therefore, in that direction, the apparatus would register 100% 0. Okay? But this is not the case. You never find, whatever attempt you do, any direction in which you have 100% 0. In fact, if this was the case, you would have a variation with theta and phi until you get to 100 and 0. Okay? On the contrary, you get always uniformly 50-50. Okay? Which means that this is not representing our state of the atoms. So what is the solution here to this problem? How should I describe the atoms there? Not with a single wave function in some sense. Okay? And the solution is with a density matrix. Okay? I will show you now how to do that. Okay, so let me just eliminate for just a short while this thing, and let us go back to our beloved pure states, okay? The psi's, okay? Let us look again at what it means to calculate the average of an operator on a certain state. So according to our previous theory, this is just that. Now, let me use any arbitrary basis. So an arbitrary orthonormal basis, let me call it phi alpha. Alpha is a label, can be anything. A set of integers, many of them, I mean, continuous, and it's just a label for an orthonormal basis that you select as you wish. Okay, so I know that the identity is the sum over alpha of phi alpha, phi alpha. Again, sum just to indicate. It might be sum and integrals. All right. So you can insert this wherever you want. For instance, here and here. And this is, as you know, a good way of transforming operators and vectors in abstract sense into matrices and vectors in the usual linear algebra way. Indeed, if you insert this thing in two places, you will have a certain sum over alpha, okay, of psi phi alpha alpha A. Then you will have another index that you should put, say alpha prime, phi alpha prime, phi alpha prime psi. And for one thing, you immediately see that here you have, say, the matrix A alpha alpha prime appearing. And here you have the vector, say, psi alpha and the vector psi alpha prime. Or better, if I call this psi alpha prime, this is really the star. Okay? This is psi star of alpha. Okay, so I might write this expectation value as a vector, a matrix, a vector, okay, in the usual way. But this is not what I wanted to tell you. This you already know. Let me rearrange a few of these things. So for instance, let me put this in front, okay? So I write this as sum over alpha and alpha prime. So I have the matrix A alpha alpha prime. And then I have an object. Let me write this first and this afterwards. So I write phi alpha, psi, and then I have psi, alpha prime, phi alpha. Is this clear? I just moved things a little bit, okay? So the matrix, rather than in the middle, I put it in front. The last thing I put immediately after, and the first goes to the end, all right? Now, look at here. You recognize something we have already encountered. Psi, psi, the projector, okay? Remember, a projector on a state psi is nothing but psi, psi. Okay? Good. And we know some properties of this projector. For instance, we know that p psi squared is just equal to p psi. So projecting twice is useless. Just one time is enough. Okay. Now, you recognize immediately that, therefore, this is really an operator, p psi, sandwiched between the state phi alpha prime and the state phi alpha. So in some sense, as I define here the matrix A alpha alpha prime to be the operator A sandwiched between alpha and alpha prime, in the same spirit, I can relabel this to be the operator P, the matrix associated to the P psi in the basis with the label, with the indices alpha prime alpha. Okay? Now, you see immediately that, therefore, here I have really the product of two matrices. You see that the index here is the same. So what I have here is the sum over alpha of the product of the matrix A times the matrix of P psi, element alpha alpha. Is this clear? Because you see I have the same element here and there. Okay? So the sum over alpha prime is simply the product of the two matrices. And the first and the last indices are the same. Okay? Is this clear to everybody? Yes. Then you see immediately that this is just the trace of the product of the two matrices, that representing A times that representing the projector. Okay? So this is another way, fancy perhaps, but totally equivalent way of expressing the average of A. Okay? So it's the trace of the matrix of A times the matrix of the projector on a certain state. Okay? Is this clear? Now, I will define this object here. For a reason, I think it's this object here is, for me, our first example of a density matrix. Okay? It's a very peculiar density matrix. It's a density matrix that recovers our usual friends, the states. Okay? So in some sense, I will, from now on, try to reinterpret everything is in here as a density matrix. So obviously, the case I have until now is a density matrix equal to a projector. Okay? Okay. One obvious property of a density matrix of this type is that the square of rho is just equal to rho. Okay? Another property is that the trace of rho should be equal to 1. Why? Well, let us apply the very definition. So I have to calculate the sum over alpha of the matrix element on any given basis phi alpha of this object. So this is psi, psi. I immediately see that this is nothing but the square modulus of phi alpha psi modulo square. Okay? But I can always prove that this is equal to 1. Why? One way of proving it, for instance, is just to shift these things. And you see that you can rewrite this as psi sum over alpha, phi alpha, psi. Okay? So rather than calculating the trace, now I'm putting the thing in the middle. But now you realize that this is the identity. Okay? So this is equal to psi, psi. So if the state is normalized, as I always assume, the trace of the projector should be 1. Okay? So I've just recalled, just renamed P rho, and therefore the trace of rho should be 1. Okay. All right, until now? I mean, this is just a change of names. Okay? P psi, the projector, I've called it rho. Now, follow me in a kind of evolution. Obviously, I have a few examples in the notes of, states, psi in different representation and writing the corresponding rho of psi. Maybe I will return to this in a second. Oh, yeah. For instance, suppose that I have the state psi that I wrote before. So some alpha plus times the state plus 1/2 plus alpha minus times the state minus 1/2. Okay? The spin part. Now, let us try to calculate what is the matrix rho alpha alpha prime, where alpha is any indices, any of this index, okay? So alpha, oops, sorry, there are too many alphas here. Let's call this coefficients A plus, A minus, okay? All right, so I want now the matrix representing, in other words, I want, this could be plus or minus 1/2, and this plus or minus 1/2 in the basis Z, okay? So I want to calculate alpha Z, the state psi, alpha prime, state Z, okay? So where this is the spin state. For instance, suppose that I take plus and plus. So the element, there are 2 by 2, 4 elements, right? Which I should calculate. Let us calculate this, plus and plus. Well, I should then take the overlap of this with the plus, which gives me a plus, and take the same overlap and now star, okay? So what I get is A plus modulo square. Is this clear to everybody? No. Good. Very good. So this object here, okay, is nothing but, so the matrix, so rho alpha prime is the matrix phi alpha projector on a state, so the state psi, matrix element phi alpha prime, okay? Now, for me, phi alpha now is this state, okay? So phi alpha, the basis, is just plus 1/2 and minus 1/2, okay? It's a 2 by 2 space that I'm working in, okay? So the resulting matrix here will be 2 by 2. This clear? I mean, I'm simplifying things. Rather than being an infinite dimensional matrix, I'm making it 2 by 2. Can you complain about this? No. Okay? So it's a the spin space is a 2-dimensional Hilbert space, and therefore, rather than having a sum over an infinite number of things, I have just 2 states, the plus and the minus. Okay? And I'm calculating the 2 by 2 matrix associated to a certain projector, psi, where the state I am projecting on is this. Okay? So this is the problem I am setting. I have to calculate, therefore, all those elements where this runs over plus and minus, over the basis element. Okay? So let us do it. I said, okay, let us calculate first plus 1/2 psi plus 1/2. Okay? Which means take the state, make an overlap with plus 1/2. Okay? So it means this is going to 0, you get A plus. Okay? So this is A plus. Then take the same object and star, because this is the star. So A plus star. Right? A plus star. So the modulo square. And I put here in the first slot of this 2 by 2 matrix. All right? Now, let us do, for instance, this element. So the element in which I have minus and minus. Then I have to take the psi, take the overlap with the minus, which means this, okay, and star it. So A minus star. The result is that what I have here is A minus modulo square. And what about, for instance, having here the plus, so the first row, second column? Well, then I would have A minus star, but the first would be A plus, okay? So here I have A plus, A minus star, okay? And if you do the calculation here, you get exactly the star of that. So I get A minus, A plus star, okay? So this is the 2 by 2 matrix. If you give me two coefficients here for the state, this is the 2 by 2 matrix representing the projector on that state in the basis of the standard spin state up and down, okay? So as you see, it's a matrix which is usually full of numbers, okay? But notice that the sum of the elements in the diagonal, which is the trace, is 1, okay? And you can verify that if you calculate the square of this, you get just the same matrix, okay? So try, I mean, if you don't believe, try. Okay. Particular case of obviously is what we have, so the parameterization we have given, cos, sine, e to the I phi. You can just do for that, for instance. Okay, so this is just an example. Now, let me just erase for a second. I will return to this example in a while, but let me just proceed with the general theory for a second. If I know that I have a certain state, then I can calculate the average of an operator A. But suppose that I really don't know that I have a given state. I know only in probability. I know that I have a certain state psi I with a certain probability Wi. Okay? So W, this weight W, is the probability that I have a certain state. Okay? So in some sense, how should I describe my system? Obviously, this might be a certain number. So I can be from 1 to a certain number n row, say, or it could be 2 or more. Okay? So I don't have a certainty of which is the state. There could be 2 or 3 or more candidate states, each of them with a certain probability. Now, this is a probability in the usual classical sense. Okay? So the sum of this thing obviously should be just equal to 1. Question: how do you describe your system? Well, if I have this state here, I know how to calculate the average. Okay? It's just this. But I know that this means the trace of the matrix representing A times the matrix representing P psi I. Okay? Now, given that the fact that if I have this state, I can calculate the average, okay? If I know that I have this state with a probability Wi, what would you write to be the average of A? I repeat again. I know that I have psi I with a probability Wi. I know also that if I have psi I, the average of A is this. Then what would be the average, grand average of A? I mean the average over state and probabilities would be the sum over I from 1 to n row of the probability of having psi I times the average I have if I have psi I, right? So times this object, the trace of A times P psi I. Okay? Is this clear? So you immediately see that I can rewrite this as a trace of A times a matrix, which is now the matrix rho, where rho is the sum over I of Wi the projector on the state psi I. Is this clear? So I moved from having a single projector to having a linear combination of projector on several states with amplitudes, well, with the weights, okay, which sum to 1. All right? So obviously the case where I have only one state, okay, the previous one is a particular case where W1 is 1 and all the other W's are zeros, okay? And I have again our previous case, okay? But you realize that this must be the generalization, okay? If I have some ignorance of what is the actual state, okay, I can restate the problem in terms of a certain probability of having certain states, and obviously the average will be now the trace of A times a new object rho, which is the combination of the projectors. Is this clear to everybody? Now, this new rho has a couple of properties. The first is that the trace of rho, okay, is still 1. Why? Because the trace of this thing is the sum over I of Wi times the trace of P psi I, which are all 1. Okay? The trace of a projector is always 1. Okay? You saw it in any basis. Okay. So if this is 1, this is the sum over I of the weights, which is 1. So the trace, even if you combine several of them, is still 1. However, what changes is that rho square generally is not equal to rho. Okay? This is true for a single projector, but if you have mixing many of them, in general, you have different from 0. How do you prove, different from the original thing? How do you prove that? Well, rho square, let us try to calculate rho square if rho is a sum of several things. Now, you have sum over I, sum over j, from 1 to n rho. Then I have Wi, Wj, P over psi I, P of psi j. Okay? Now, you realize that if you act projecting, let me assume that these states are orthogonal to each other, okay? So the psi I and psi j are orthogonal if I select several. If they are not, I can always subtract an appropriate things in such a way that they are orthogonal. Okay, so this psi I are orthogonal to each other means that if I is different from j, I'm projecting on a state and then on some orthogonal state. But once I project on a certain state, nothing is, the action of the orthogonal projector gives you 0, okay? This means that the only term surviving here is just the diagonal term, okay? Where I have sum over I from 1 to n rho, Wi square times the projection twice on the same state, which I know it's just the projection once, okay? So you see immediately that rho square has a similar look to rho, but rather than having Wi, you have Wi square. This has a deep consequence. The trace of rho square, for instance, if you calculate, will be just the sum over I of Wi square. And you realize immediately that if I have a certain number, n rho of weights, which all sum to 1, then the sum of their square will not be 1, okay? Because they must be all less than 1. So when you square, you get less. Unless, obviously, these are not really different from 1. There is only 1, which is 1, the other are 0, then the square is just the same thing, okay? So for the general case where these numbers are different from 1 and zeros, then when you square them, you get less. So the trace of rho square is less than 1, with the only exception of being equal to 1 when when the state is a pure state, okay? So this, the equality, I call pure state this, pure state, which means a density matrix where the rho square is equal to rho, okay? And mixed state, anything else. So mixed state, a matrix like this where the Wi are all different from 0, okay? I call it mixed, all right? So in a mixed state, I have the trace of rho square less than 1. For a pure state, it's equal to 1. Okay? Is this clear? Okay. Now, what is the state, now that you know the theory, of the spins entering the Stern-Gerlach apparatus? We proved before it's not a pure state, right? Yeah.
Here, I runs from 1 up to n rho, right? What if n rho is like infinity? I mean, if the states are,
Well, obviously, n rho cannot be as large as the Hilbert space. I mean, usually the ignorance is not that large that you really don't know which state in the Hilbert space. I mean, this number is not, for instance, in the case of spin, n rho can be at most 2, okay? Because obviously there are no more than 2 linearly independent spin states, okay? In a 2 by 2 state. So for the spin case, this is just 2. In general, I mean, you can write, the theory behind this is subtle. You can write several representations by changing the psi of the same density matrix with different initial psi's and w, okay? So it's a bit subtle how many. There is a minimal number, okay? And I think that there is a theory for that, but we will not really. There is a minimal number but you can be more, I mean, you can add other unnecessary things in the sum, okay? There is a minimal, and I think that there is a precise theory of how to get what should be the minimal number of states appearing. Okay. So for the spin case, if n rho is 1, I have a pure state, and we discussed cannot be, because otherwise the pure state should be in some direction, theta and phi. I rotate the apparatus, and I should get 100% and 0. And in any case, under rotation, the thing should not be uniform. It means that it must be 2 in that case. There must be 2 states, 2 spin states, which I must sum, okay, to get the density matrix. You might say, okay, which ones? Okay, let's try. Maybe the solution is just that psi 1 is the state plus 1/2 z, and psi 2 is the state minus 1/2 z. Okay? And this is with probability 1/2, and this is with probability 1/2. Okay? So if this is the case, what would be the density matrix associated? Now, you remember probably that the general solution was that the density matrix associated to a given state, a given projector, was just the following: A plus modulus square, A minus modulus square. Then I have A plus A minus star, A minus A plus star. This for a given thing, okay? So for instance, if the state is purely up, so if I have the state psi 1 equal to plus 1/2, then here I would have a 1, here a 0, here a 0, and here a 0. Okay? So the matrix would be 1, 0, 0, 0. Okay? If the state would be psi 2, which is minus 1/2, then the matrix would be 0, 0, 0, and 1. And if I have this with probability 1/2 and this with probability 1/2, the density matrix describing the state in this basis is just 1/2 times the identity. Okay? Notice how big is the difference. The trace is 1. Okay? Has this. This is also trace 1 for any arbitrary alpha plus and alpha minus. However, you see big difference. Here, there are no off-diagonal elements. Here, in general, if there is an alpha plus and alpha minus that are different from 0, for instance, 1/2, this would be different from 0 as well. Okay? So a pure state would have off-diagonal matrix element. The mixed state, which is 1/2 up plus 1/2 down, has just elements in the diagonal. Now, if I calculate with this mixed state, so to repeat is W, so it's 1/2 the projector on the state up, so psi plus 1/2 plus 1/2 plus 1/2 the projector on the state down. Oops, it's written very badly. Okay? Then, if this is the matrix, the density matrix, I know that I get this element representation. So if I ask you to calculate, for instance, what is the average spin, what is the average number of atoms I would get in any of the two spots if I analyze with respect to Z, what you predict is just 1/2 and 1/2, right? Is a reasonable thing. But there is more than that. You can calculate that the trace, the expectation value of any other rotation of the Stern-Gerlach apparatus would still give you 1/2 and 1/2. Okay? How can you prove that? The proof is pretty simple. After all, this rho is written in the basis of the plus 1/2 Z and minus 1/2 Z. Okay? So it's very simple to calculate, for instance, any property of the spin along Z in this basis. But if you want the property of the spin along any other direction, I would rather use as a basis to express everything the basis of the eigenstate in that other direction. Okay? But if you rotate a basis, okay, from, say, Z to N, and you have a matrix that is essentially the identity, is a multiple of the identity, can you tell me what is the matrix representing rho in the new basis? It's just the same. Okay? The matrix that is identity, you can rotate it in any spin basis and will appear always the same. Okay? So the matrix representing rho in any possible basis of spin eigenstates is always this. And you realize that, if you think just a little bit, that the average that you would need to calculate to tell me the number of atoms ending in one of the spots will be uniformly 1/2 and 1/2. Okay? So this must be the solution to the Stern-Gerlach problem. The atoms enter the apparatus not in a definite spin, but 1/2, loosely speaking, in a certain spin, and 1/2 in any other direction orthogonal to that. For instance, 1/2 up and 1/2 down along Z or along X. Okay? Doesn't really matter because, whatever is the basis you use, it's always that, the matrix representing the mixed state. Okay? So not a pure state, but a mixed state is what describes the atom entering the apparatus. And this perfectly fit with the results of the Stern-Gerlach experiment. Okay. Now, these density matrices are very important in at least two other contexts. The first is the following. Suppose that you do statistical mechanics. Then obviously you know that you have a certain probability of having states. In classical terms, there is a probability of having a certain energy that is given by a Boltzmann factor, okay? Well, in fact, in quantum, for a quantum system, the quantum distribution is exactly identical, okay? So let us consider a certain Hamiltonian H, okay, time independent. You know that this will have certain eigenstates, phi alpha or phi n, always oscillates in the number, in the labels, okay, with certain energies En, okay? In other words, H phi n is equal to En phi n. Now, the Boltzmann factor probability would be e to the minus En over kBt. So this is the probability Pn of staying in a certain eigenstate En. Now, you might tell me, wait, this is not the probability because it's not normalized to 1. Correct. You have to divide by some number, which is equal to the sum of all these things. So you immediately realize that Z should be equal to the sum over n of e to the minus En over kBt. Okay? What is this? The partition function. Okay? So this thing here is what is called the canonical ensemble. In other words, the canonical ensemble tells me that if I have a certain Hamiltonian at a temperature T, I should not describe the state as being in any of the states of the Hamiltonian, for instance, but being really in a density matrix which is equal to the sum over n of this probability Pn times the projector on the state phi n. Okay? Now, you probably have seen this, but in a slightly different way. I want to convince you that this is nothing but a different way of writing e to the minus h over kBt divided by z. Okay? As an operator here. Notice, until now, we have seen exponential of operators to do the time evolution, where, however, here I had I t over h bar. Okay? Now I have, for the first time, an exponential with a minus in the temperature. And I want to show you that these are just the same object. Let's see. In order to prove that they are the same object, it's enough that you calculate matrix elements and you prove that the matrix elements are the same. Okay? So let me calculate now the matrix element of this object between a certain state phi n prime and the state phi n. Okay? What is it? It is 1 over z, a constant, e to the minus h over kBt. But I know that phi n is an eigenstate of h with eigenvalue En. So this is equal to e to the minus En over kBt times the same state. Okay? So when I go to the matrix element, I get delta n n prime. So this is equal to the delta n n prime, then e to the minus n over z, so Pn, the probability. Okay? Now let us look at this on the left-hand side. Is this clear to everybody? No, I see some phases not completely. I took this operator, okay? And I calculate the matrix element between n prime and n, where phi n are eigenstates of the Hamiltonian. The result was simple because since these are eigenstates, I have just e to the minus the eigenvalue times a delta when I take the thing, okay? But e to the minus the eigenvalue divided by the partition function is according to this prescription, which is due to Gibbs, obviously. This is canonical ensemble. It's just the probability, Pn, of being in the state n. Okay, now you can do this from this is now our current view, sum of certain probability times projector, what we did today, except that rather than having just a finite sum, now in principle I have a sum over the whole Hilbert space. This is an answer to your question. In this case, you have to sum over the whole Hilbert space, okay? So it's a mix of all possible eigenstate Hamiltonian with weights that are, however, Boltzmann weights. Okay, it's very simple. Let me call this sum over n second. Okay? Now let me calculate the matrix element with phi n and phi n prime. Well, you immediately see that out of the sum, the left and the right-hand side forces n second to be equal to n. Otherwise, I get 0, right? So n second must be, I get a delta n second n. But once I have this delta, I mean that I must have only one term surviving, which is Pn, phi n, and this gives me 1. And then I realize that this gives me an extra delta of n prime times Pn. Exactly what I have there, okay? So this sum of probabilities, Boltzmann weight, times projector is nothing but a different way of writing the exponential of the Hamiltonian, this time with minus and 1 over bt. Okay? Is this clear? No. Good. Where? It's not clear. From the beginning.
No, this sum outcome is equal to delta n.
This? Okay. Because this is a probability. Oh, sorry. These are operators, okay? These are projectors. This Pn here are now. I should call them probably Wn, the weight, okay? This is probably slightly more clear as a notation, okay? After all, I had called them W in the previous thing, okay? So, first of all, I realize that there must be a delta of n second and then n, okay, which means that only one term is surviving, which is this. And then I have, so let me substitute here everywhere, W. And then I have W, which is a number, times this scalar product with that. But if n prime is different from n, I get 0. So there is a delta of n prime Wn. And on the right-hand side, I have exactly the same expression. Okay? So this proves that these two objects that look slightly different, in particular, the exponential of the Hamiltonian seems a very simple object. This seems a very nasty infinite sum of projectors. They are the same thing. All right? Okay. Now, what I have explained to you works not only for Hamiltonian of a single particle, it works really in general terms, okay? Quantum statistics, the canonical ensemble, more precisely, of a quantum Hamiltonian is just defined in this way. This is the Gibbs canonical ensemble. So you calculate a partition sum of all eigenvalues weighted in this way, over all states. And then you calculate probabilities, and then you essentially have the exponential of the Hamiltonian to represent your mixed density matrix. All right? Now, you shouldn't think that this is a very simple thing to do. Okay? Given a system, this is a complicated thing. First of all, because it's complicated, generally speaking, to calculate the eigenvectors and the eigenvalues. Second, because you have to calculate a partition sum. Third, because then you have the exponential of the Hamiltonian to work with, which is not simple, even that. Okay? So, I mean, it's a series of complications which can make life not trivial in general. However, we will do next time in detail the following exercise. Suppose that H was our beloved harmonic oscillator Hamiltonian, okay? So in appropriate units, this Hamiltonian, you remember that if I select units of length equal to the oscillator length and units of momentum appropriately, then the Hamiltonian is essentially this times h bar omega. So I know how to solve everything. I know the eigenstates, and I know the eigenvalues. In fact, the eigenvalues, you know, are h bar omega n plus 1/2. Now, for this problem, I can therefore ask you, what are the averages now in the mixed state at temperature T? Okay? So you know, for instance, in the ground state, how to calculate averages. You know how to calculate averages in any of the state psi n, in principle. Well, phi n, I called phi n. Okay? Remember, phi n are just your beloved a dagger to the power n over square root of n factorial applied to phi 0, to the ground state. Okay? The thing that you have already worked a lot in the midterm exam. Okay? So these are eigenstates of the Hamiltonian with eigenvalue En equal to h bar omega n plus 1/2. Okay? So it's reasonable to ask, for instance, what is the average energy? What is the average H? According to what we have developed so far, this would be the trace of the energy times rho, where rho is the exponential of the energy with the minus sign divided by kBt. So can we calculate the average energy of an oscillator at a temperature T? This is the exercise that we'll do next time. Now, if this was classical, you would know the answer, right? Because you know that any degrees of freedom, okay, on average has an energy kBt over 2. And the equipartition would tell you that I would have an average energy of kBt. So half and half. All right? So the average energy would be kBt if this was a classical oscillator. But now it's a quantum oscillator. Okay? So you have to do the exercise. Not difficult, but it must be done. In particular, you understand that there must be deviations from kBt. Why? For instance, suppose that the temperature was 0. In the limit of 0 temperature, which of the weights dominates? Let's see. The one with lowest energy. So the ground state in the limit of 0 temperature will acquire a weight 1, and all the other states will acquire a weight 0. All right? So in the limit of 0 temperature, this mixed state becomes a pure state, which is the ground state of the quantum Hamiltonian. And you know that in the ground state of the quantum Hamiltonian, the energy is how much? 1/2 h bar omega. So immediately realize that if I have here, for instance, kBt over one-dimensional. This is one dimension. Yeah. Okay? So if I calculate the average energy, for t going to 0, this should be 1/2 h bar omega. On the contrary, when t is much larger than h bar omega, I expect that this thing will go like KBT, okay? So KBT. So evidently, there must be some freezing of this. If you prolong this KBT all the way, you will get to 0, which means the particle in the origin with 0 momentum, okay, at temperature 0. This is not true because there are quantum fluctuations and the energy is just finite, okay? So how to describe this? The calculation is needed, and this can be done. We'll do it more in detail tomorrow, perhaps, but you start doing, please, so that you confront yourself with the difficulty that you would need, okay? So just to tell you something, you should try to calculate, for instance, since the Hamiltonian is A dagger A, the Hamiltonian is h bar omega A dagger A plus 1/2. Why don't you try to calculate the expectation value of A dagger A? In other words, the trace of this object times e to the minus h over kBt divided by z. See if you can calculate this, okay? And you should find something interesting, which is the Bose-Einstein distribution function, or the Planck distribution, which is the same, roughly the same thing. Okay, and by the way, this is at the heart of the black body problem. Okay, in some sense, the black body is electromagnetic radiation. The energy of electromagnetic radiation has all frequencies. Okay, but each frequency behaves as an harmonic oscillator, in some sense. Okay, and the thermal average of this harmonic oscillator is not classical; it's quantum. In particular, all frequencies, okay, which are much larger than the temperature, okay, so if the temperature is much less than the frequency, you expect strong deviation from classical behavior, okay? So the large frequency part of this spectrum will tend to show you quantum effects, okay, at any temperature. So you can have a black body radiation hold at a few hundred degrees, which is a large temperature, never mind. There are frequencies that are much larger of that KBT, which will show you quantum kind of freezing, okay? And this will determine the fact that the Planck distribution is different from the classical form that Wien or whoever were the black body people had determined, okay? All right, so this is a very useful exercise. So try to sit down and think what you should do. Tomorrow we'll do it together. Yeah?
What is this frequency? Because we say for lot of temperature. I thought it is related to temperature. But what is this frequency? Because I thought it was related to the temperature.
The question is, what is this frequency? Because they thought that it was related to the temperature. No, this is the frequency of the oscillator, okay? There is a mechanical oscillator in this case, or a electromagnetic oscillator, which has a certain frequency, omega, okay? This is given. Then the temperature is another variable, okay? Now, depending on the relationship between how big is this energy, h bar omega, and how big is the temperature, you can be essentially in two regimes. A classical regime, okay, if the temperature is much larger than h bar omega. This means essentially that many eigenvalues are all occupied because the spacing on the scale of t is very, very small, okay? So it's almost like a continuous spectrum. Is this clear? H bar omega is much smaller than the temperature, which means very, very fine distribution in the spectrum. On the contrary, the temperature is much smaller than the spacing. It means that you see the spacing, you see the quantum nature, the discreteness very well, okay? So these are the two limits. Classical limits where you don't see the spacing because your temperature is much larger than the splittings, or quantum limits where the temperature is much smaller than the splitting, okay? And in the middle, obviously, there is a crossover, where in principle you should do a quantum calculation, but you tend more and more towards the classical solution, okay? So this is a very useful exercise because it shows these two limits, how to recover classical physics at very large temperature from essentially having not so much sensitivity to splittings if your temperature is so large, okay? Now, before ending this lecture, I want to show you another instance where mixed states, density matrices are important, okay? So the first is this, statistical mechanics. There is another one, which is in some sense very fundamental. If you look at a certain system, okay? Oops. Your system is, say, A. Oops. I was calling A before an operator. Okay. Well, let me call it calligraphic A. Okay. So this is a certain system composed of some particles, which are the system you would like to study. Okay, in your experimental chamber. Obviously, outside, there are many other particles and people and apparatus and things that surround your system. You call it B. Okay? So, in some sense, the Hamiltonian of the system is made of the Hamiltonian of A, the Hamiltonian of B, and some interaction between A and B. Okay? Now, however, you want to measure only properties of B. The question is, how do you describe the properties of B? With the pure state or not? The answer is no, in general, with the density matrix. Even if the state of the whole universe, okay, suppose that I have the state of my whole universe to be just one big state psi, a pure state psi. Suppose I know the Hamiltonian of the universe and the state of the universe to be psi. Then question, what would be the state of my small system A? Now, in the process of tracing out the rest of the system except A, I'll show you that from a pure state, you generate a mixed state. Okay? So the answer is that rho describing A is mixed. Okay? Not a pure state, even if the Hamiltonian and the state of the whole system is pure. Okay? So how to do this? Well, the Hilbert space of my system is HA. The Hilbert space of the rest is HB. The Hilbert space of the whole universe is HA times HB. Okay? Remember this usual tensor product we found for orbital and spin pieces of the wave function. Okay? Now we are extending this to a more ambitious thing, so a system and the rest of the universe. Okay, so you know to write any function, any state, right? Suppose that I have here a certain basis. Let me call small phi. Let's see. I will call this small phi alpha A. Okay? Hopefully the notation is clear. This is a basis all related to subsystem A of states labeled by some alpha. Alpha could be anything again. Okay? In the same spirit, the rest will have also a basis, which I will call big phi beta of B. Okay? Okay? So notice with small and big, I will also typographically distinguish a little bit the two as you make. But the most important thing is that I associate alpha to A and beta to B so that you clearly see which is which. But to reinforce, I also make it capital and I also put A and B there. Okay? So there should be no confusion. Good. Now, given the structure, you know that the most general state in this Hilbert space is really equal to a sum over all possible alpha and beta in these two sets of the state phi alpha A, the state phi beta B, times a coefficient, which in general depends on the alpha and beta values. Okay? This is the most general state in this tensor product. Okay? This is a fancy terminology that the mathematician would use in this case. Okay? I have two Hilbert space. I can make a tensor product of the two in this way. Basis of the one, basis of the second, and the most general state in the product is just a sum of the states. This is exactly what we wrote already for orbit and spin. Notice one thing. Unless this coefficient here are very special, this is different from a state of the first times a state of the second. Okay? You can immediately tell me that if these two things are product, for instance, suppose that this was a certain coefficient A of alpha times certain coefficient B of beta, okay, then I would be able to separate the sum in two pieces, and I would write this as the sum over alpha of A alpha phi alpha A times the sum over beta of B beta phi of beta B. Okay? Which is a state of system A times a state of system B. All right? So if this is the case, I say that the state is separable. Okay? This is an example of a separable state. If you cannot find any possible basis in which the state is of this form, you say that the state is entangled. Okay? The state is entangled otherwise. Okay? Now, hopefully it's clear that there is some freedom in choosing this phi alpha basis and big phi alpha basis for these two subsystems. Okay? So by changing basis, maybe I can find an expression for this psi which is separable. But if I cannot find any possible basis of A and B such that the coefficients that describe psi are products in this way, then I say that the state is entangled. Okay? So you start to understand that the question of deciding if a state is entangled or not is subtle, because maybe it doesn't look so entangled, but by selecting an appropriate basis, it is separable. Okay? So it's a complicated thing in general. Okay? But now let's see if we can answer this, for instance, by some property. And I anticipate to you the following thing. If I calculate a trace over the B states, okay, of the psi, I will obtain, for describing my system, a density matrix, rho, okay, which is pure only if the state is separable, okay, and mixed otherwise. Okay, so in some sense, by doing this process, I will be able to answer the question if the state is not separable or yes. Okay, now, this is just this general setting. Let me just show to you the simple, the simple way of tackling this problem. Looking at a certain subsystem means that all measurements that I make refer to operators A, which simply look at this part of the system. Okay, for instance, the energy of that system, the angular momentum of the system, any quantity that refers only to this Hilbert space, okay, and not to that. Okay, for instance, in the case of orbital and spin, any quantity that depends on the orbit or on the spin. Okay, only one of the two and not the other. Okay, so the question I want to ask is, what happens to the average of an operator on the full state psi, but the operator only acts on a certain part of the system, A? Can we calculate anything? Yes, we can, obviously. Let us start from the very general expression of psi. Let us put it there, and it's simple to show that this is equal to the sum over alpha and beta from this piece, right? Then I would have, let's see, some C alpha beta, and then I would have the operator A and the state phi alpha A, phi beta B. Okay, to the right. To the left, I will have a similar expression with another alpha prime beta prime appearing, C star alpha prime beta prime, and then I have here phi alpha prime, phi beta prime. Is this clear? Okay? This is just a straightforward consequence of this. Now I use a consequence of the fact that A only acts on A type of system, okay? Which means that these two guys don't do anything. They just watch each other, and in the middle there is nothing that regards them, okay? Which means that beta prime and beta must be identical, okay? These two states must be the same. And this, on the contrary, is just the matrix element of A. Okay, so I can rewrite this thing as, you see that I have a sum over alpha and alpha prime. Then I have the sum over beta that really is confined to this piece, right? Because there is no other beta around. And then I have the matrix phi alpha prime A phi alpha. Okay? Is this clear? These are matrix element of the A subsystem. Okay, good. Now, you see that this has exactly the standard form, okay, of the trace of A times rho. But what is rho? Well, it takes a second to see that rho of alpha prime is just equal to the sum over beta of just what you have there. C star alpha prime beta C alpha beta. Okay? So the matrix element of the of the density matrix, which represents for me the sum, is just equal to this object. So in some sense, you can view this as a density matrix living only in here, okay, but you can test immediately that this is not a pure state, unless obviously the state is separable. If the state is separable, then this thing here would be a sum of A alpha times B beta, and this would be A star alpha prime B star beta, but the sum over beta of this would be just 1, and therefore this would reduce to essentially to something like A star alpha prime A alpha, which is the matrix element of a pure state, really. Okay? So if I have, which is this, okay? The state only. The matrix element that appears there is this, just the projector appearing there. So, all in all, mixed density metrics appear every time you look at a piece of the system which is in some sense not separate in this sense from the rest of the system. So the ignorance you have on what the environment is going to do on the system is encoded in the fact that you don't describe the system as a pure state, but in general as a mixed state. Okay? Oops. Well, there are a couple of more things that can be said from here, but I think that this is enough for today. Maybe I take again this tomorrow and I show you that this is indeed a mixed state. So I should show to you the trace of rho should be 1, which it is, and the trace of rho square. I will do that tomorrow, okay? Yeah. On this? This is clear, the first expression. You just take this expression for psi and you put it there. Then I notice that A watches only what A does and not B. And therefore, beta and beta prime have to pair among themselves in this matrix element. Okay? Producing a delta of beta prime beta and disappearing. Okay? So these two things disappear, giving me a delta of beta prime and beta. If I use that delta, beta prime beta, I can essentially reduce this double sum to a single sum. And the coefficients there now have beta prime equal to beta. You see? I have used the same beta. All right? And now I notice that here there is no longer a beta. So the sum over beta is confined to the coefficients. No. I assume that all the measurements I make, so all the operators that I'm going to consider, A, are only looking at this part of the system. If I start looking outside, there is no clear separation between A and B. Okay? This is important. So if I always and only look at things that happen here, then I can essentially trace over. You see, this operation here is like tracing over the rest of the universe, leaving only as information these matrix elements here, okay, which, however, in general are not a state, but a mixed state, not a pure state. Is this clear? So by looking only at the piece, I can trace over the rest, but the price to pay is that the state of this piece is not a pure state, unlike the full state psi, but is rather a mixed density matrix. Okay?
From the start, if A didn't act on B, why would I use, why would we include the states?
The question is asking, if A doesn't act on B, the measurement, why should I even think of introducing anything else but the system? Okay, this is your question. This is a very legitimate question. In other words, I'm looking at a certain apparatus, and I measure only things of this. Why should I care about the rest? I mean, the operators certainly act on a Hilbert space of this piece. Yes, but who told you that the state of this system is a state living in just the Hilbert space and the pure state in that Hilbert space? We don't know, right? That is exactly the difficulty. The system is perfectly described by a certain set of measurements and so on. But who tells me what the state that the system is going to be? What this thing shows is that even if the state was a perfect pure state at the level of A plus B, then generally speaking, I should expect the state of A to be a mixed state rather than a pure state. Okay? That is the whole problem. I have no guarantee that the state of my little system A is a pure state, in other words, whenever there is something else in interaction with A, which is always there, because, I mean, nothing is isolated in the universe, okay? So this is only to show that, in general, I should expect systems to be described by mixed state. And only under certain appropriate condition I can neglect this mixed nature and talk about pure state, okay? So the rest of the universe usually has the effect of producing mixed state for the system you look at, okay? So tomorrow I will return to this again, maybe to show you a little bit more, and we'll do the exercise of the quantum oscillator. Okay? So that's it. Yeah. Yeah. The question is, if the states are separable, what do I get? Well, what do I get is that essentially this matrix, this density matrix is simply a pure state density matrix, and therefore the average that I should calculate is simply equal to sum over alpha and alpha prime of A star alpha prime, the matrix of A between alpha prime alpha, A alpha. In other words, just what you would calculate for a pure state system and an operator living in that system A. Okay? So this would be what you would calculate before today's lecture. Okay? I give you a state, I give you an operator, and you calculate the average. Now you realize that this is only a particular case, okay, of a more general setting in which your system might be in interaction with something else that I trace over the something else. Generally speaking, what I get is a density matrix and not a pure state. Okay? All right. Maybe reiterating tomorrow, okay, by successive approximation, I will get the message through. Tomorrow I will do it again, and I will show to you that in general the trace of this thing, the trace of rho square is less than 1 unless you are in a separable situation. Okay?